Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 5.21. The problem statement says, in froth flotation, air is bubbled through an aqueous solution or slurry to which a foaming agent, soap, has been added. The air bubbles carry finely dispersed solids and hydrophobic materials, such as grease and oil, to the surface where they can be skimmed off in the foam. An ore-containing slurry is to be processed in a froth flotation tank at a rate of 300 tons per hour. The slurry consists of 20 weight% solids. The ore, specific gravity equals 1.2, and the remainder are aqueous solution with a density close to that of water. The slurry consists of 20 weight% solids. The ore has a specific gravity of 1.2, and the remainder an aqueous solution with a density close to that of water. Air is sparged, blown through a nozzle designed to produce small bubbles, into the slurry at a rate of 40 feet cubed at standard temperature and pressure per 1,000 gallons of slurry. The entry point of air is 10 feet below the slurry surface. The tank contents are at 75 degrees Fahrenheit, and the barometric pressure is 28.3 inches of mercury. The sparger design is such that the average bubble diameter on entry is 2 millimeters. Part A, what is the volumetric flow rate of the air at its entering conditions? Okay, so you've got air getting blown into this column at this standard temperature and pressure per 1,000 gallons of slurry. We have this much slurry going in. This is the weight% breakdown of what that slurry looks like. What happens is you have the bottoms come out the bottom. Those are more highly concentrated, like heavy water soluble, or not even necessarily water soluble, but water non-hydrophobic, hydrophilic solids want to come out the bottom. And then you've got your hydrophobic, small, fine ground ore that is bound to an oil, wants to stick to the outside of the bubbles and foams up to the top. And then those bubbles are skimmed off, and then you have a concentrated ore slurry coming out the top. So instead of having a 20% solids ratio, that changes because you're going to separate some solids out the bottom and the top. But we're going to assume that this solid to water ratio is kind of similar going through the whole column. But yeah, you do have solids, and you have water coming out the bottom and the top, but the ore is going to be like the part of the solid that you want is going to come out the top. That's the purpose of this unit, is to concentrate the solids that you want and remove the solids that you don't. So in copper ore, typically you bind the copper to the bubbles, and they come out the top, and then the bottoms you get like the clay and the other kind of junk solids that you don't need, they call it, and I think it eventually goes to tails. Okay, so if you ever see like tailings piles at mines, that's what this is coming out the bottom. We've got the ore specific gravity, we have water specific gravity. We know that the height of where the bubbles are coming in is 10 feet, and that the bubbles down here have a diameter of 2 millimeters. Okay. Part A asks us to, what is the volumetric flow rate of the air at its entering conditions? They gave it to us in STP, so we're just converting STP into whatever conditions we have. And the conditions that we have are this temperature and this pressure, sort of this pressure, not actually this pressure, but at this temperature is what we're going to assume. Remember, this is the atmospheric pressure, so we convert that. Also, they gave it to us in non-SI units, so I just convert everything into SI units. So feet turns to meters, temperature turns to Kelvin, Fahrenheit turns to Kelvin, and then inches of mercury turns to pascals. So that's what all this section is for. The next part we have to say, okay, standard pressure is 1 atmosphere, standard temperature is 0 degrees Celsius, so we turn that into Kelvin. Then we've got our standard conditions applied to the ideal gas law. Then we have our ideal gas law applied to the real conditions. And we're just going to do ratios of that so that we can convert our volumetric flow rate from standard conditions into the actual conditions. And we're going to assume that the molar flow rates of these two streams are going to be the same. Okay, so a lot of this cancels out, and you end up with just a ratio of temperature, pressure, and volumetric flow rates. So then you can just calculate what the real volumetric flow rate is. Here's the problem. We don't know what the pressure is where the air enters. We don't know what the pressure is right there. That's why they gave us the height of this column and the density information, okay? And then we also know what the atmospheric pressure is, okay? So now we need to know, well, what is the pressure where the air is entering, okay? Pressure is equal to the atmospheric pressure plus the height of the liquid column, okay? And this is going to actually be slightly different because you're going to have air in there, a certain amount of air being pumped in. So I didn't consider that in my analysis, but you may be able to factor that in. But I'm just going to assume that the whole thing is not going to be affected by the air that's in there, and that might be a bad assumption. If you guys come up with a better way to account for that, and I may look at that later, where you also account that there might be that this density is going to be affected by the air that's in that column, then yeah, let me know what you think in the comments, and then I can also go through this problem again and see if I can try and factor that in if you guys are interested. But anyway, we're going to say, okay, this is the atmospheric pressure that they gave to us. The column of liquid is equal to the acceleration of gravity, that's g, and this is the height. We converted that into meters, did that over here, g, h, and then we're going to assume that the density is just a combination of water and solids according to this ratio, okay, and so we're going to assume the whole column is just full of the slurry, okay, and so they mix together according to this ratio so that the mixture of the density is going to follow this rule, okay. So this is the density that we calculated, and we use that to calculate what the pressure is down at the bottom, right here where the air enters, okay. Then we have enough information to calculate our volumetric flow rate. We put in all of our parameters here, and we calculate that the volumetric flow rate is 0.984 meters cubed per 1,000 gallons of slurry. Okay, well, let's convert that volumetric flow rate into something that's more relatable instead of per 1,000 gallons of slurry, because they gave us our processing rate, that it's 300 tons of slurry per hour. So let's go ahead and factor that in. So let's convert these units. We've got per 1,000 gallons of slurry, there are this many gallons in this many meters cubed. Then we know the density information, and we know the mass flow rate, so then we can convert that, convert the tons into kilograms, and then all the units work out to where we're left with meters cubed. Okay, so then we get that there are 68 meters cubed per hour air flowing out of the nozzle. Part B, by what percentage does the average bubble diameter change between the entry point and the slurry surface? Okay, so remember the bubbles going in are at 2 millimeters diameter. Okay, what size of bubble are they when they reach the top of the column? Because the pressure is changing significantly as it flows back up because of you have this column of liquid sitting over it. Again, we're going to assume that the density is uniform throughout the column and it doesn't change based off of the size of the bubbles and things like that, nor how much air is being pumped in there. Okay, well, we know that the volume of a sphere is this function. This is 4/3 pi times the radius cubed. Okay, so I'm going to convert that into a diameter, a function of diameter instead of radius, and we're left with this. I'm going to say 1.1 is where the air is injected, and 0.2 is at the top of the tank. Okay, so the volume of the bubble at 0.1, where the air is injected, and then the volume of the bubble at 0.2 at the top of the tank, where the foam is getting skimmed off. Okay, the temperatures are equal. The molar flow rate is equal. We're going to assume that the bubbles don't merge together to form larger bubbles as they would typically in this. So we're just looking at a single bubble and assuming that it doesn't combine with other bubbles, so it's going to have the same amount of moles of gas going up as it travels through the column. But we know that the pressures are not equal, right? Okay, so this becomes a ratio of pressures. How does the volume change? Well, it only depends on how the pressure changes. We solve for what the volume of a sphere looks like. Okay, so we're going to plug that into this and we get that it's just a ratio of the diameters cubed. Okay, so we're going to take the cubed root of both sides so that we can just get the diameter ratio, because that's what they were interested in. And we know what pressure 1 and pressure 2 are. This one's the atmospheric pressure, and this one is the pressure where the nozzle is getting injected. Okay, and we get that there's a ratio. The density ratio is equal to this. Okay. They asked for what's the percent increase, or they asked for what's the percent change, and we know that it's an increase because this number is larger than 1. So we say the percent increase is equal to this ratio minus 1 times 100%. Okay, and the percent increase is 9.8% increase. So the diameter is going to increase by 9.8% as the bubble travels up through the column. All right, that is it for problem number 5.21. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.